Okay, hello everyone. Welcome to day 3 of Code Astro. How's everyone feeling this morning? Woo! Here we go, day 3. Day 3. Okay, so we'll just start off with our introduction slides and some announcements. Um, First of all, remember this afternoon is a free afternoon, so there are no optional lectures today. And we actually have an in-person, well, for the folks that are in person, we have a workshop dinner tonight at 5:30 p.m. If you look at that conference logistics webpage on the website, you'll see details. But it's going to be located just right here out in the yard, right? The lawn?
Yeah, like right to the right here. And it's free for everybody attending the workshop, whether or not you're staying on campus.
Okay, so yeah, so definitely we'd love to see you for the dinner. Just be sure to bring a jacket. As you may have seen these last couple days, right? Things can get chilly in the morning and they can get chilly in the evening. Um, and we just wanted to remind everyone to kind of be connected with our community on Discord. And just to remind you some important Discord channels to explore, right? We do have a mental health Discord channel, as well as a memes and a Pets of Code Astro. So I encourage you to check out these different channels on the Discord.
I've seen nearly enough memes this year yet. It's y'all to get working on that.
Yes. Sarah is challenging the class of 2026 Code Astro to up the meme game here. So let's see what y'all come up with. Now remember, we do have this anonymous feedback form, so please fill this out as often as you want. We do really pay attention to your feedback, and every year we're constantly tweaking things to make this workshop as useful as we can for all of you. Here we go. We also remember we have our class-sourced vocabulary list. If there's ever a term that we say during a lesson that you don't we haven't really talked about yet, be sure to check out this vocab list and it'll give you a little bit more information. But always, of course, feel free to ask questions during lectures for vocab you don't understand as well. Okay, so that's a good segue. How to ask questions. Well, please ask questions often. We have many different ways to do this. For folks remotely, you can use the chat box on Zoom. We also have for everyone the Piazza channel, the Piazza website. And remember, on Piazza, you can choose to raise a question anonymously if you feel more comfortable that way. And then, of course, Discord as well, right? We have that Ask Questions channel on the Discord. Us instructors, the TAs, we're all monitoring these different avenues, and we'll try to answer questions as quickly as possible. Okay, and just a reminder, we're day 3 into the workshop, right? What are these overall goals? By the end of the workshop, we hope that you'll be able to use the language of software development, develop and release an open source astronomy package. This is the project you've been working on so far. And 3, we hope that you'll be able to write code that follows the best practices of software development. And then specifically today, we have a couple different goals. One of our goals, we're going to be talking about documentation. So how can you use doc strings to document your code, and then use automated tools like Sphinx in order to compile those doc strings into a nice website for your users. We'll also be talking about how to set up and release your Python packages publicly, like, for example, so that it becomes pip installable. In terms of your projects, we don't have a specific goal for today. Remember, this afternoon, we kind of mean as a break. So feel free to recharge, relax, and go out and do something fun this afternoon. And then remember, in the evening, for the in-person folks, we'll have our conference dinner. Okay, almost there. So before we get started, remember with your Code Astro repository, you want to make sure you have the most recent version of the Code Astro repository. In order to do that, you can go ahead and CD, right? Move into your Code Astro directory. And then we're going to use this series of commands to save any local changes that you've made to your repo, right? You use git stash, that will kind of save your local changes off to the side. Once you do that, you'll be able to do a git pull origin main to get the most updated version of the repo from the origin up on GitHub. And then if you use the command git stash pop, that's going to reapply your local changes. That way it doesn't mess anything up. And please, if you run into any problems with this, please feel free to ask a TA. Okay, and I think that's the last slide. So I think the first lesson we'll be doing today will be with the releasing code. Is that true? Yeah, okay. And so with that, I will pass things over to Sarah for the releasing code lesson.
All right, cool. So it's day 3. We're going to tell you how to make your code pip installable today, about releasing it to the universe. I've got a new meme for you. I didn't make it, but I really like it. Let's take a minute to appreciate it. Yeah, I like that one. Also, shout out Gus Spring. All right, so importantly, I want to also remind you that you belong here and that I know this is hard. There's a lot of new stuff. You're sort of drinking from the fire hose this week. But even though these things that you're learning are hard, they can all be learned and you're all learning it. We're very happy to have you here and you all belong here. All right, so let's dive into the lesson. By the end of the lesson, you'll be able to state the purpose of a bunch of different files, pyproject.toml, init.py, license, and readme files. You'll be able to package a Python project for broad distribution and make your code publicly available on PyPy so it can be pip installable. Just to give you a preview of the activities you're going to be working on, you're going to create a pyproject.toml and init files for your package. You're going to package and upload your code to PyPy using Twine. You're then going to release your code on GitHub, and then you're going to create a Zenodo digital object identifier, or DOI, to make your package citable. And then optionally, you can add badges to your README file. People often feel like nervous or embarrassed about releasing their code if they feel like it's sort of buggy or it's unfinished. I want to encourage you all to release your code, an initial version of your code, even if you feel like it's not like ready for public consumption. A really common way of doing this in like industry is releasing version like 0.0.1 of your code, and people will recognize that that's not like your official first release. Your version 1.0 can be like, this is my official release of your code, 0.0.1, and then if you have subsequent releases like 0.0.2, whatever, people will recognize that that's not like the first usable version of the code. It's important to practice releasing your code, so that's why we're sort of pushing you to do this, even if you feel like it's not ready. All right, so let's first talk about why we bother releasing code. One thing you can do is just put your code on GitHub and then have people, git clone it and use it however they want. One reason to make it pip installable or installable with another utility is you get control over how the code is actually set up on somebody's computer. So if you want them to, for example, download some data files that are included with your distribution, if you want them to compile some code, like you have some C code, for example, you can do that all in a pip installation. You can also keep track easily of versions of your code. So you can track your code you can sort of publish and then make citable your code at different specific like checkpoints or versions. And then also it's just sort of like expected nowadays. Like a lot of people expect your code to be able to be pip installed. So it makes it easy for users to install and use packages. It's just generally a sort of convention nowadays in astronomy. Okay, so first a little bit of vocab. What is a package? A package is anything in the Python world that's installable. So packages package related code together in one place. So you can have lots of different files, lots of different modules that comprise a package. Another thing that's useful about a package is you have these dotted naming schemes. So if two different packages have the same module, like named utils, for example, you can import orbitize.utils and radbuild.utils, and those won't conflict. They won't clash in the namespace. This is not true of all languages. R in particular always really bothers me because you just import something and you don't maintain the name of the package, and so you get conflicts in your namespaces all the time. So I don't know. I have lots of gripes with R in general. Okay, so I've said this word module too. So what is the difference between a module and a package? In general, in the Python world, a module is any individual Python file. So a package is a collection of Python files, and they have an init.py at the root. So init.py, we're going to talk about in a couple slides too, is a file that like tells Python this thing is a package. All the files in this directory comprise a package. So from least information to most information, you've got individual variables, then functions and classes, then modules, individual Python files, and then packages. So this really confused me when I started learning about this. This is sort of like a random point of interest, but I always include this slide since it was very confusing to me. Python treats both packages and modules as type module, even though they're called different things in the docs. So if you import a package, Orbitize, which has many files, and you print out the type, it'll say that's a type module. And if you also import an actual module of a package, it will also treat that as type modules. If you want more information about Python packages and modules, there's a link here. It's kind of just like random specific stuff, but figured I would mention it too. Okay, so here's a sort of typical organization scheme for a Python package. We've got our top level package here, and then we've got an init.py at the root. So this is what communicates to Python again. This is a package. Everything that's in the same directory as this sound is can be imported as one package, import sound. You can also have sub packages. So each sub package also has to have an init.py at the root, so it can be imported by itself as an entire package. And then we've got individual modules in each of these sub packages here. So the way that you would then import this, given this file structure, is from sound.effects. So that's the Python sub package that you're importing. Import echoes, that's then the module that you're importing. And then you would do, if you're calling like a class or a function that's defined inside of echo, you would say echo dot whatever the name of the class or the function is. One other thing that is sort of a non sequitur, but I feel like doesn't really fit anywhere else in Code Astro, is to mention auto formatters. So if you, there are a bunch of auto formatters that are integrated really easily really nicely into VS Code nowadays. They can make your life easier by automatically applying formatting rules. Not everybody uses these or wants to use these, and different packages have different like conventions, but I figured I'd just show you how this works. So I want to do a little demo of Rust, which is a particularly fast auto formatter. Sorry, rough. It's written in Rust. It's not actually called Rust. Let me exit and change that. Now it's not letting me exit. Okay, I'll fix it after. It's not Rust, it's rough. Okay, so you can install rough in this extensions tab here. So we're in this part of VS Code. It looks like this. In general, I disable it for the Code Astro workspace so it doesn't automatically format things, but let's show what happens when we enable it. So I'll enable it. I'll go back to like broken orbitize.py, and then I have it configured to format on save. So that means that I'm going to do file save. Just kidding. Oh, okay, it already did it. Okay, so if it was like this before, I save it, and then you can see it changed a couple of small things. So it made it so that this line wasn't longer than 80 characters. It also included a space between the top comment and the first import. So this is a Python convention. It'll also organize your imports. So for example, if we put orbitize.kepler before numpy, when I save it, it'll switch them back around. So this is a nice thing you can choose to enable if you want. Okay, rough demo. All right, cool. All right, so now we're going to talk a little bit about different files that you need in order to release your code on PyPy. The first thing we're going to talk about is init.py. So this little like organizer here is taking you through all of where all of these different files live in the normal structure of a package. So Generally, you have a top-level directory called the name of the package. So in this case, it's my package. And in it, we've got a license, a README, things like requirements.txt, pyproject.toml, and then you have two subdirectories. One that has the same name, also my package. So in Orbitize, we have a top-level Orbitize directory, and then another Orbitize directory that's inside of the first Orbitize directory. You'll also see this in some cases called source or SRC. This is where you have the init.py file, all of your other code files, and then you might also have a separate test directory that has pytest files. We're going to talk about testing in pytest tomorrow. All right, so let's talk about init.py. I've already sort of gone over most of this, but an init.py file lives in the same directory as your code files. It's sort of analogous to the init method of a Python class. So essentially, just any commands in that file are executed whenever someone imports your package. And the other thing is that this communicates to setup tools, which is the tool that Python uses to install packages, one of the tools that Python uses to install packages, that the code in this directory is a Python package. So I'm going to do a quick Orbitize init demo to just convince you that this works. So let's go back here. All right, so I'm going to open Orbitize. So you can see here's the top level directory of Orbitize itself, and then we also have a subdirectory called Orbitize. We also have a subdirectory called tests. We've got a bunch of other stuff. We then have our README, pyproject.toml, license, all at the root directory. So if we go into Orbitize and we go into our init.py file, all of this stuff are things that are going to be executed every time someone imports Orbitize. So just to show you that this works, I'll add a print statement here. And hello code Astro. And then I am pretty sure I have installed IPython. I should have checked this. No, I haven't. Sorry, live demos. It's of course going to take like a million years too. Okay, just kidding. I'm not going to do this now after all, sorry. Okay, just trust me that if I were to open IPython and just import Orbitize, it would print out that print statement because it's executing all that code in the init.py. Sorry, I should have tested that demo. Didn't think about that. Okay. Okay, so the next file I want to talk to you about is pyproject.toml. So a pyproject.toml file lives in the root of your repository, so at the same level as your the directory that contains all your code files. Not in that directory, but at the same level as that directory. It's going to specify how your project will be built on a new machine and also defines metadata about your project, like the name of the project, who wrote the project, all that kind of stuff. So this is the most minimal pyproject.toml script. You can do all sorts of more fancy things with pyproject.toml to give you more control over your setup, but this is all you need for a basic setup. So the first thing you have is your build system. We generally recommend using setup tools. There's a couple different ways to install actually automate the setup of your Python package. The main differences between them are just that some of them have features that others don't. It changes very quickly. So sometimes some of them, a month ago, one setup tools didn't have, some particular capability, and then a month later it will have some capability. So usually I recommend setup tools unless you have some explicit reason why, you want to use a different distribution. If you do want to use setup tools, this is exactly the little bit of the script that you need. Then you have the metadata about your project. So you've got the name of the project, the current version of the project, and then a list of your dependencies here. So dependencies are any packages that you need to install in order to use your package. So anything you import in your package. So if you use NumPy, then that makes NumPy a dependency of your project. One hot tip is to use underscores instead of dashes when you're defining the name of your project. Dashes, for whatever reason, in Python lead to some annoying behavior in certain contexts. So there are several different ways that you can install Python packages. The PyProject.toml framework is pretty new. And so the community is currently transitioning from generally using a script called a setup called setup.py rather than transitioning from setup.py to PyProject.toml. Currently, PyProject.toml doesn't have PyProject.toml is more like a list of keywords for things that setup.py will then do. Sorry. It's a list of keywords that setup tools will then do. Setup.py is a Python file. So there are still some things that you can do in setup.py that you can't do in PyProject.toml. So you'll see older projects like Orbitize still have both a setup.py and a PyProject.toml. But for new projects, it's recommended to have only a PyProject.toml. But I just wanted to explain, if you see this is a sort of older convention. If you want to see a minimal example of a working package that can be pip installed and that only uses PyProject.toml, there's a GitHub repo that I've got here, solid octo fish stick. That was another one of the GitHub auto-suggested names. But yeah, that's all you need in order to make your package installable. Okay, so let's now talk about license and README files. So the README.md, which stands for Markdown, is what users will see when they open your package on GitHub. So let me show you what the Orbitize README looks like. You've also probably gotten familiar with these already through Code Astro, because we also use READMEs. All right, so when we open up our GitHub page and we scroll down, you can see that the README is here. There's a bunch of different stuff here. We've got a couple of different badges that link to the current version of the code on PyPy that can be pip installed, link to whether our docs are currently building, continuous integration tests, which we'll talk about tomorrow, and other things like the Zenodo DOI, which is something that makes the code itself citable, and the license. This readme.md lives in the same root directory here. So if we were to open it and look at the actual raw markdown, this is what it looks like. So it'll just display nicely on the homepage of your GitHub repo. The license file is some legal mumbo jumbo that copyrights your open source code, gives you legal rights over your work. This is a really nice link that'll sort of walk you through, based on how you want to use and distribute your code, which license is right for you. It's really important to include a license, because if you don't include a license, people can't legally use your code. So there are lots of different licenses you can use for lots of specific different situations. If you don't have a strong opinion, two of the most common licenses for astronomy code are BSD and MIT licenses. I've got a link here that takes you through some differences if you're curious. All right, now let's talk about requirements.txt. So requirements.txt is a list of Python packages your package needs to run, or dependencies. You might be thinking, wait, didn't we have that in PyProject.toml? Why do we need a whole separate thing for to list your dependencies again? This is also sort of a historical thing. Requirements.txt used to be used directly for installing your package rather than this thing in PyProject.toml, but it's falling out of common use. However, a lot of services still expect you to have a requirements.txt. So as far as I know, Sphinx, which we're going to be talking about later today, which is a tool that helps you build a documentation page for your package, is going to expect you to have a requirements.txt file. So for all intents and purposes, this can be the same as the list of dependencies in your PyProject.toml file. So you can basically just list the dependencies twice. Strictly speaking, you have to think about which services are actually expecting you to have a requirements.txt file. So for Sphinx, for example, this is everything you're going to need to build the docs for your package. So you might not actually need every package that you need to run your package in order to build your docs. All right. Question?
The advantage of requirements text is you can pip install it quite easily. So let's say you were cloning someone's, too much importing it. Can you do that from a pyproject.com, or is it harder to install the dependencies properly if you wanted to just clone something and work on it as well?
Yeah, so the question was, one nice thing about requirements.txt is you can like pip install -r the requirements.txt file before you actually pip install the package itself. Can you do that from pyproject.toml? I don't think you can do it from pyproject.toml. I'm not 100% sure. In general, you should be able to like pip install the package, and it should like auto install all of the dependencies too. So it shouldn't, strictly speaking, be necessary to pip install the requirements before you install the package itself. But it is like a nice feature to be able to have. Yeah. This is also like one thing about, the community transitioning between between conventions for doing these things, is that there's like some bits of functionality that are still sort of being translated to the new formalism.
Best practices question. How many other packages can I have as a requirement for my own package?
Yeah, that's a great question. So the question for folks online was, how many other packages can you have as dependencies for your own package? So there's a couple different things to say about that. I don't think it's like inherently bad to have dependencies. Like generally, especially in Python nowadays, like it's pretty hard to like write a project without NumPy, for example. I think in general, like having a lot of dependencies makes your package a little bit more brittle, meaning that like if a dependency breaks, then your code also breaks. So if you have like, 30 dependencies, you're more likely to have something broken at any given time. It really depends on like how much functionality you need from those dependencies. So if you need if you're using like one function from a dependency, it might be better to just rewrite it in your own code so that you don't rely on that dependency. It makes you sort of less brittle. But if you're using half of the code in a package and your package is really built on top of that package, then you really do need that as a dependency. Yeah, I don't know. Do you guys have any other thoughts on that?
It's kind of vibes based maybe, but if you are installing just if there's a package that has a lot of dependencies itself that takes a while to install and you're only using it for one thing, or maybe you have like a side feature that you don't expect most people to use, but then comes with a bunch of dependencies, you may not want to include them for all users to install, and then just have documentation to tell users to install these things if they're going to use this thing.
Mm-hmm.
I've seen environments that you can specify versions of packages, but I haven't seen that in the tunnel. And from experience, I know that like what you just said is accomplished. So isn't requirements then more powerful in some sense?
Yeah, good question. So the question is, you can specify versions of packages in requirements.txt. Can you do that in pyproject.toml? You can do that in pyproject.toml. So you can specify versions of packages. You can also specify like minimum versions or maximum versions. So it has to be like at least NumPy 2, for example. Another thing you can do is to specify a dependency from GitHub specifically. So if you don't want it to look on PyPy where pip packages live, you can just have it like download and pip install something from GitHub directly. Yeah, good question. All right. Okay, so that's pretty much it. That's all you need in order to make your package installable. The first thing you can do is once you create your pyproject.toml and init.py files, you can actually test your installation locally. So the first thing you do is just cd to the directory containing this pyproject.toml, and then you type this command, python -m pip, or just pip install -e space dot. So -e means that any changes that you make subsequently to this to the code is going to be reflected on disk. So for example, if you don't include the -e, if you pip install your package, it's going to like freeze the version of the code at that given time. So if you then go into your package and like change something, that change is not going to be reflected in the version of the code that you import. So -E means that like the package is actually going to be like rebuilt on your disk every time you make a change to your code. If everything goes well, your package should be installed. You can now import and run your code from anywhere on your computer. It should automatically be added to your path. Yeah. Okay, so you've now made your code pip installable. How do you make your code publicly available? You haven't necessarily made it accessible for other people to pip install. You have to use the internet in order to do that. So the way that you do this is by uploading your code to PyPy. So I've mentioned PyPy a couple times now. PyPy stands for the Python Package Index. It's a software repository for packages written by the Python community. Pip, which stands really amazingly for pip installs packages, is the package installer tool associated with PyPy. So PyPy is like GitHub, pip is like Git. So pip is a tool, PyPy is a place repository. We've also had you using Conda for a lot of things. Conda is a general purpose package management system. So Conda also comes with things like Conda environments, for example. Pip doesn't have any like environment management capabilities. Conda does have some capability to install certain packages. So Conda can install NumPy, for example, and it can install AstroPy. Generally, community developed tools like Orbitize are only going to be available on PyPy and not on Conda. If you want more information on pip versus Conda, I've got a nice little link here. Another thing that I wanted to mention is that there are a couple new package managers that are really rising in popularity over the past like year or two. And you saw me actually use one of them just now when I tried to get my demo to work and failed. So that maybe wasn't the best advertisement. But so these are called UV and Pixie. So these are both new package managers that are rising in popularity. One of the reasons that they're becoming more popular is that they're both written in Rust, which gives them a really major speed boost over pip and Conda. So if any of you like waited a really long time for something to install with Conda, using UV and Pixie, UV or Pixie, gives you a significant advantage in that regard. UV is sort of like the Rust evolution of pip, and Pixie is sort of the Rust evolution of Conda. Strictly speaking, I think Pixie has like a superset of the functionality of UV, but UV is actually, I think, more popular. It's got a sort of simpler and cleaner design. If you're curious about like, there's a lot of like historical reasons for the fact that there are all of these different tools and like a lot of them have the same functionality. If you want to like take a deep dive into the history, this is a really good article that takes you through not just UV, Pixie, Conda, and pip, but also like Mamba and what's the other one? Poetry and all sorts of other things. All right, so how do you actually make your code available on PyPy? That's good. I'm glad you like that one. This is a very vintage meme. This one might be from 2020. All right, so how do you make your code publicly available? So we want to make it so that from any computer, someone can just type pip install the name of your package, and then it'll automatically install it the way that it would on your computer. So we recommend using Twine, which is a useful utility for uploading to PyPy. So you first have to build your code for distribution. So this is basically just making it's making something called a wheel, which is like a compiled and compressed version of your code that can be then uploaded to the internet. Someone else can download that and then expand it and install it. So first you need to install two tools. You need to install Twine itself and then build, which is a Python tool for building packages. You then, from the root of your directory, you type python -m build, and that's going to create these wheels. And then you do python -m twine, upload dist. And dist is where your built files are going to go. So you're taking those things and you're uploading them to PyPy. And that should be it. So I want to give you a quick set of advice about GitHub releases and versions. So we also recommend that every time you make a significant change to the main branch of your repository, you should release a new version of your code. And releasing a new version means putting a new version of the code on PyPy so that someone can pip install that particular version of your code. GitHub releases is another way that you can keep track of different versions of your code. Strictly speaking, you don't have to do both of these things. You could either do GitHub releases or you could do PyPy installs. They're basically just different places where you store like a frozen version of that version of your code. GitHub releases, yeah, what was I going to say? Oh, the best practices for these are to keep your GitHub releases and PyPy releases consistent. One of the worst bugs I ever encountered in my whole life was I was using a pip installed version of somebody's code, but I was looking at the version on GitHub and the versions were inconsistent. So the code that I was looking at was not the code that was installed on my computer. So don't do that. That was terrible. That took me like 2 weeks to figure out. So keep your releases consistent. My workflow is that every time I release a new version, I'll upload the new code to PyPy, I'll release the new code on GitHub. Nowadays, there are actually GitHub Actions that can do all of these things for you automatically too. We'll talk more about GitHub Actions tomorrow too. Another best practice is to maintain a descriptive change log somewhere in your documentation. And this will be like, in this version, which was released on this date, we made these changes. These will also be like, in your commit messages in GitHub, but it's nice to make it like very easily human readable and like a summary in case you have like, 20 Git commits that like, is it working? Now it's working. I don't know. Is it working? Is it working? So here's an example of our change log. So here's the version of the code that we released, the date that we released it, and like a description of what changed, and then who actually made the change. So yeah, so that's what that looks like. Oops. Another question we get all the time is about version number. So what does it mean, like 1.2.4? Generally, you increment the first number for a major functionality change, especially if backwards compatibility is lost. So that means like if someone wrote a script using the old version of your package, that script might not work anymore with the new version. So a really big example of this was going from Python 2 to Python 3. So in Python 2, there were a lot of differences in Python 2, but one really major one was that you could print things with print space and then whatever variable you wanted to print. In Python 3, you couldn't do that anymore. You needed parentheses, print parentheses, whatever you wanted to print. So that meant that a lot of scripts written with Python 2 wouldn't work once you went to Python 3. So that was one of the big reasons that they incremented that first major number from Python 2 to Python 3. The second number is for a minor functionality change. So for example, if you add a new feature, you don't lose backwards compatibility, but your code can now do something new. And then generally the last number is for like a small bug fix. So something that's not going to significantly change the way your code is supposed to work, but maybe makes it better. Generally, I don't release new versions if I just make change to the documentation, but you can. It's sort of up to you. Okay, so I also briefly mentioned Zenodo. Zenodo is a way to make your code citable. This is particularly valuable if you you should make your code citable right away. You don't need to like wait to publish a paper about your code in order to like get citations for your code. In astronomy and academic astronomy, like citations are important and they help you get jobs and stuff. So you should be accumulating citations for your code. This is a link about how to set up Zenodo to automatically archive a new version of your code every time you release it on GitHub. That's another reason that I like to do GitHub releases, is because it syncs to Zenodo. I also want to show you Orbitize's Zenodo page. So if we go back to our README here, this DOI down here takes us to Zenodo. All right. So this is the record. We've got like the particular version that it's recording, the authors of the code, and then this is like a frozen version of v 3.3.2 of Orbitize that's all zipped up. So if someone wanted to go back to that particular distribution, they can. This is also important because the Zenodo sort of committed to like long-term maintenance of these things. This is that you can think of this as like long-term storage of these different frozen versions of your code. And then one other nice thing is that if you scroll down here, you can see the citation and you can export it in whatever style you want. You can also, if you want it in BibTeX, which often we do in astronomy, you can just export it in BibTeX directly or copy it. All right. The next thing I want to tell you about is the Software Citation Station, which is something I just found out about this year, which is really, really cool. This is a project led by, I forget their name, so I'm going to just go to there and tell you the names. Tom? I think it says at the bottom, yeah, Tom Wagenfloor. Okay, so the Software Citation Station, you can select the software that you're using, say you're using AstroPy, select the version of AstroPy you're using, and then also the version of the dependency that you're using. And then it automatically generates the acknowledgement and the BibTeX that you need in order to include it in your paper. So this is really handy. I think this is also a really nice initiative for just making software more easily citable in general. I think one thing that tends to happen is people tend to cite like the software, the main software they're using, but not the dependencies of that software. So you don't necessarily cite NumPy, for example. So I think this is a really nice way to automate that process. We just added Orbitize to it, so it should be here. Yeah, so you can see it. Yeah, so I definitely encourage everybody to like use this when you're citing software, and also upload your own software to the citation station. It was very easy for me to like follow the process that they recommended. All right, I also want to give some opinions about publishing software papers. I think it's really important to say that it's worthwhile to make your code open source, even if you don't plan to publish an associated paper, or even if you don't think your code is very good. A lot of times people say, like, I don't think my code is well written enough to be public. I think anytime you make your code public, it will end up being useful to somebody, even if you don't think it's like up to your own standards. That's different from like, you know, making like, I don't know, proprietary data public. Like you don't have to make every single thing public in your research, but I do encourage you to make software public wherever you can. So worthwhile to make your code open source, even if you don't plan to publish a paper. However, if you do publish a paper, it can be really good for a lot of different things. So one of the things is it's really good advertising for your code. Like a lot of people in our community read the archive, and so they'll see, oh, there's this new code that's published here. It looks like it contributed to X, Y, and Z cool results. Maybe I'll think about using it for my own work. And another thing is that it gives some people something else to cite when they use your code for their own work. Got some examples of software papers in astronomy. All these three are older papers that were published before like I think Orbitize was the latest one published, and that was like 2020, I think, or 2021. So these were not published in software-focused journals. They were all published in like astronomy journals. But nowadays, another really great option for publishing software is JOSS, the Journal of Open Source Software. I really like JOSS for a couple of different reasons. JOSS has a public review process. So the review happens in GitHub issues. So the reviewers will actually like comment on the code, give suggestions. The authors of the code will respond. And another really nice thing about the JOSS review process is that it's not just the paper that's reviewed, but also the code itself is reviewed. So you'll get advice on the structure of your code, etc. So I've got some examples of the JOSS review for Orbitize v3, all of the comments that were made and all of the responses we made, and then also an example of a JOSS review that I refereed, so a different paper, and then the suggestions that I made, and then how the authors responded. Mm-hmm.
Did you submit any manuscript for each version, or did you just have one?
Yeah, good question. So the question was, do you submit a new manuscript for each version? No, you don't have to submit a new manuscript for each version. We have a a GitHub action set up so that it recompiles the paper every time we submit a new version. But honestly, it's probably not necessary. Like the manuscript doesn't change with each new version. You can publish new JAWS papers for new versions if you want. So this is one of the reasons we decided to do this for Orbitize v3 because we included like a bunch of new capabilities since Orbitize v1. So we thought that JAWS would be a good like venue for publishing that. But yeah, you definitely don't have to. Yeah. That's another nice thing about Zenodo is that like you don't have to write anything. You just make like, if someone used v3.2, they can cite that specific version that they used. Yeah, great question. Thanks.
So I just clicked on the link of the JAWS paper you
Mhm.
Is that how it's usually done? The reviewers are also known and it's different from how I expect a regular academic journal review process.
Yeah, so the question was, the like JAWS review looks very different from the classic academic review process. And one thing in particular is that the identities of the reviewers are known. Yeah, that's very typical. And it's like sort of it's a trademark of the JAWS review process that everything's open and everybody's known, which I think there's, pros and cons to that approach, but that is definitely the way that it's done. Yeah. All right. Almost through. I just wanted to also briefly advertise. We had a past TA, Paulina, who wrote up an excellent Jupyter notebook in Spanish, taking you through the process of releasing your code. Paulina basically translated the majority of the Code Astro materials to Spanish. And if you don't know Spanish, you should learn. All right, so that's pretty much it. Let me hide this. All right, so the activities to work on with your project groups. You're probably not going to make it through all of these things right now, but start now and then continue, not this afternoon since it's a break, but tomorrow afternoon, are to basically make your code pip installable. So create pyproject.toml and init.py files for your package and upload your code to PyPy using Twine, release your code on GitHub, create a Zenodo DOI for your package to make it citable. You can create badges for your README file. You can look at Orbitizes for inspiration. We also have a Made at Code Astro badge that we'll post in the Discord. So if you want to add that to your repository, you can do that. And then a final optional activity is if you want to check out UV, which is one of these new package managers. I've got a getting started tutorial with UV. And I'd encourage you to think about what you like or don't like with respect to Conda. There are some there's some significant differences, and I think some of them are great and some of them are not as great. And then just quick reminder again, I know I said this before, but we encourage you to create an initial release today, even if your code is buggy. It's low stakes. Nobody's going to go back to like version 0.0.1 of your code and complain that it doesn't work. All right, let's do half an hour. Does that sound good? All right, so we'll come back together at 25 minutes after the hour. All right, everybody, time is up. Remember, you can continue to work on this tomorrow afternoon. So we're gonna take a 5-minute break and then we're gonna talk about documentation, both like best practices for documentation and automating building a website for your project. All right, so let's come back together at 34 minutes after the hour.
Okay, everyone. I think getting ready. We're about ready to move on to our next lesson. We are going to be talking about documentation. And it's going to come along with a little bit of a code along demo. So like we've done in the past for this lesson, it'd be great for everyone to have 2 windows open. The first window you have open is your web browser on the Code Astro GitHub page. Let's go ahead, go to the day 3 folder. And in the day 3 folder, you'll find this subfolder called tutorial doc. And inside tutorial doc, there is a readme.md. This is where we're going to be working from today. As you can see, there's an excellent meme go along with this lesson. but the second window you want to have open is your VS Code, and then go ahead and open that tutorial doc folder inside the Code Astro Day 3 folder. Go ahead, open that in your VS Code window. We'll use that in a little bit. But for now, while everyone's getting set up, I'll give everyone a chance to appreciate the meme. Okay. Great. Let me make this smaller. Yeah. Okay. Great. So documentation, right? When we start talking about documentation, we often get reactions like this, right? But if we're all honest with ourselves, we all know how important that documentation is, not just in the context of open source software, so other people can use what you write, but also for yourself, so you remember the functionality of the code you wrote 2 months ago, or in my case, the code I wrote 2 days ago. So there's many different types of documentation. Here, I'm going to make this bigger. There we go. Okay, so there are many different ways you can document your code. First way is by using what's called inline comments in your code, right? So this is inside your .py file. You're writing type. You write a line of code to do something, and then you just you include a comment, which is led by this pound symbol here, that just has a string that explains what the chunk of code you just wrote actually does. Oh, uh-oh. Yeah, so that's one way to document. We won't be talking too much about inline documentation today. Second way you can document code is by using what's called doc strings. And you've already seen a few examples of doc strings throughout Code Astro, but this is chunks of comments that occur at the beginning of a function or a class definition. And we're going to talk a lot more about that in a little bit. Okay, but other than inline comments and doc strings, other ways you can document your code is by using README files, right? A README file, this will just be a text file or something like that that comes along with the code. Maybe that has installation instructions or some top level idea to give users how to use your software. And then finally, not finally, I guess there are lots of ways to document code, but the other one we want to highlight here is documentation pages, right? This is having a website that documents the functions in your code and how the user can use those functions themselves, right? Okay, so Jason has some hot takes on documentation, and I happen to agree with them, so we're going to talk about them here. So hot takes on documentation. Number one, perfect is the enemy of the good, right? So some documentation is better than no documentation at all. We're going to talk about best practices and different things you should have in your documentation. That's something to strive for, but it's okay if you don't cross all the T's and dot all the I's. Having some documentation is going to be super critical for your users. Now, documentation that you should, the types of things that you should really include in your documentation. One, you want to tell your users how can they set up and install your code, right? Ideally, you could just set up give some examples of commands that someone just can copy and paste in their command line, and it'll just install your code, right? But this is great. So how do users set up and install the code? You also want to make sure in your documentation, you tell users, how do you run your code, your software, in the most common use cases? Examples of this can be a Jupyter notebook that just says, hey, here's an example. I'm going to import the code and I'm going to do something cool with it. That'll really give your users a feel for how your code works. Another thing you want to document is your code's API. Now, API stands for Application Programming Interface, right? And basically all that means is it specifies what are the input variables to your code, and then what do your code outputs. As we talk about doc strings in a little bit, doc strings are an excellent way for you to document the API of the different functions in your package. And then finally, something that I think is kind of easy to forget, but it is important, especially in the thinking about open source software. You want to make sure to tell people if they use your software package, how can they cite you? How can they give you and your developers credit for the work that you've done? So yeah, these are kind of top level things, good things to include in your documentation when you're working on your packages today. Okay. But let's talk a little bit more about these Python doc strings. right? And I have an example here in the README, but the example in the README here is exactly the same. If you go into your VS Code window, right, under this tutorial doc folder, we have a subfolder called correlate. This is a little package here. And correlate.py, this has some functions relating to cross correlation. This is what we're going to be working with today. And so the screenshots I show in the demo are exactly the same as what you see on this .py file, correlate.py here. Okay, so doc strings. There's a lot of different styles of doc strings that you can use, but for the purposes of today's demo, we're going to be focusing on the Google style of doc string. Right? And so here's an example of a Google style doc string. And very roughly, you can break down this doc string into 3 separate parts. Right? The first part of the doc string, so we define this function, and then we start with 3 quotation marks. That begins your doc string. So the first part is the description of your function. All right, right after the quotes, you start with a short 1, 2, 3 word, very top level summary description. What does this code actually do? In this case, cross-core, right? It does cross correlation. And then after that, then you can add a couple strings with a little bit more details of exactly what this code is doing. Right? We are calculating the cross correlation of array B against array A. Right? Okay, so that's our description, the first part. The second part of this doc string that you can see defines the arguments for your function, right? In this case, we have A and B. It says what they are. Okay, A is the reference against which the cross correlation is calculated, so on and so forth, right? But I want to draw your attention in this doc string, maybe I'll make it a little bigger. We don't just describe what the variables are. We also define what the variable data types are going to be. In this case, both A and B, we expect them to be array data types and specifically NumPy vectors. This is really, really useful for debugging and later on. So this is something sometimes I forget. It's very useful to not just define what a variable is, also define the data type that the function expects. Right. And then the final section of this doc string under returns, this tells you, well, what does your code output? Once again, it's going to say the data type, this returns an array, and that array, in this case, happens to be a cross-correlation function. Okay, so this example, in this syntax, this is like 75% maybe of what you'll need as you're documenting your project functions here today. However, the syntax can be a little different for specific cases. For example, if you have optional input variables, if you have classes, this is a little different. If you have exceptions, things are a little different. We're not going to go into all those different permutations today, but in this README, you can see example doc strings for all these cases, all other cases as well, by following this link. All right. And after this demo, I encourage you to follow that link and take a look at all the different things you can do. Okay, great. So now we have these doc strings. You want to write these for your functions and classes, especially those that are user-facing, right? Anything that your user is going to use, you want to document the API if you can using this doc string, right? But it's not quite enough just to have the doc strings alone, right? You could imagine as a user, you're looking at this big package, there's tons of .py files. Your user is going to have a hard time sorting through all the .py files and reading all these doc strings on their own, right? Ideally, we'd also have a website or a documentation page that someone can go to and search and basically parse all of these doc strings, right? And fortunately, if we've gone through the trouble of formatting all these doc strings correctly, we don't have to do that by hand. There are automated tools out there that will automatically go through your project and build documentation pages with all the doc string information. And so what we're going to do now is we're going to demonstrate one of these automatic tools, which is called Sphinx. Okay, and in this demo, this quick start guide here, we are going to build Sphinx web page documentation for this package correlate inside the tutorial doc folder. Right, so this is why you want to have it open in VS Code here. Okay, great. So how do we start building documentation for a package? Well, here we go. I'm in VS Code here, and I have my terminal window. First, can everyone see my terminal here, or is the text big enough, or can it be larger? Okay. If folks have trouble seeing things, just let me know and I can make things bigger. In fact, maybe I'll make this a little higher, that way up on the screen. Okay. So the first thing you want to do, here we go. We're inside this tutorial doc folder. Here we go. Oh, I should, sorry. I should also say that the things that we're going to do in this code along, it is followed kind of step by step in this demo. So feel free to code along with me. But if you run into a bug or have a problem, don't worry about it. Don't try to debug on the spot. Just kind of pay attention to the rest of the lesson. And there'll be time afterwards in order to debug, and you can ask TAs and instructors. We can work together. But everything is documented in this demo, so you can reproduce it later. Okay. So what do? We are in this tutorial doc directory here. First thing, we are going to make a docs directory. And we make that by this command, make dir docs. And then we can go ahead and go inside the docs directory. All right, now we have an empty directory. And inside the empty docs directory, we can run the command sphinx dash quick start, just like that. And Sphinx, if Sphinx is installed on your machine, which it should be in your Code Astro environments, that was part of the setup, Sphinx is going to start with some feedback looking like this. Okay, so we have to set up some things for our documentation. Sphinx is going to ask us some questions. First, do we want to separate source and build directories? Don't worry about this. We'll just do no for now, just the default, so we can hit enter. Next, we have to assign a name for our project. And so I'll just call this, I don't know, docs tutorial. Okay. The next thing you do is you want to add the author names, everyone in your package, or working on the particular package. So there we go. And then the third thing you want to put in is that release number, right? Sarah just talked about release numbers a second ago. And let's just say this is going to be release 0.1. It doesn't matter what number you put for the purposes of the demo. Okay, and the last thing Sphinx is going to ask is, what language do you want to compile your documentation in? For the purposes of the Code Astro workshop, we'll use English. And so we'll use that as the default. We'll hit enter there. Okay, so what has Sphinx done? If we go ahead and do an ls and now look at what's in our docs directory, we see that it's made a bunch of files. Okay, and if we're following along with the README, we just did step 2, and now we're in step 3. Okay, so what do we do next? Now that we've initialized our documentation, we need to edit the configuration file, which is stored in this conf.py. So let's go ahead and open that in VS Code. We have our editor here. Here's the docs directory that we made. And you see let's go ahead and click conf.py. It's a little smaller, right? And we see a file that looks something like this, right? There's like a project information section, a general configuration, and then options for HTML output. Okay, so we have to make some edits to this configuration file in order for the documentation to work. The first thing we need to do is we need to add a path. Now, the path is going to tell Sphinx where it needs to go to find the package that you want to document. Now, sometimes your conf.py will have a path setup section, and then it'll have a block of code that looks like this. If you do have that, go ahead and uncomment the lines that you see. I know my version didn't automatically generate it, so I'm just going to copy what we have here, and I'm just going to paste it in conf.py just above the project information section, right? And then once I paste it in, I'm going to uncomment these lines, right? Okay, so the first 2 lines, those are import statements. Fine, we're importing packages, but that's all to set up this path for Sphinx to find your package. Okay? So after we have done that, the next thing we need to do is we need to modify the path here in order to point to the package. Because right now, right, it's just the path is pointing to the current directory, which is docs, right? But where does correlate live? If we're in docs, right, we need to go up a directory, and then we need to go into correlate. So let's go ahead and put that in. So it's ... move up a directory, and then correlate / right? And that points to where correlate.py is. That's also where your init file is. All right, so after you do that, your path section should look like this, right, under section 4. Okay, great. So we're almost done, but there are 3 additional changes we need to make to this comp.py file. The first thing under project information is we need to specify what the root page of our documentation is going to be. And so to do that, we are going to add this command right here. We're going to say it is, oops, I did that. It's right under the project root _ doc equal to index. Okay, so what does that mean? Well, if we go ahead, right, if I do an ls in the terminal window, you'll notice that there's an index.rst file that Sphinx automatically created. .rst stands for restructured text. The way Sphinx works is it uses restructured text files and uses those to build the HTML files for the web pages that we'll make in a second. But so root doc equals index is just saying, let's go ahead and use index.rst as the root page, the home page for our documentation. Okay, great. So there's the root doc. The next thing we need to do, and this is in the screenshot here in the README. Here we go. We need to go to the extensions under general configuration, and we need to add some extensions here for Sphinx. Right? These extensions we need to put in quotes here. The first extension we want to add is Sphinx .ext and then auto doc, just like that. Now, what is this going to do? This is going to give Sphinx the power to automatically read your .py files and build the documentation from the doc strings. Okay, so that's the first extension. And we're going to want to add another extension. So I'm going to put a comma here, right? New line. The second extension we want to add is Sphinx .ext Napoleon, which I always Napoleon. Yes, spelled like that. I think I did that right. Okay, what does that do? That's telling Sphinx, he gives Sphinx the power in order to interpret Google style doc strings, which is what we're using here. Okay, so those are the 2 extensions that we want. The last thing we want to do, and admittedly is the least critical, but if we go down to options for HTML output, we're going to see this variable here that says HTML theme. This is just, what style of web page do you want? For this demo, I think it's nice. Let's go ahead. Oh, perfect. I have it down here. We're going to use Sphinx _RTD, stands for read the docs, if folks are familiar with that. So Sphinx _RTD _theme. All right, and then we'll save. So those are the changes we need to make to our comp.py file. Okay, so now we are ready to make the first version of our HTML pages for the documentation. So the way we do that, let's go back to the terminal. This a little smaller, right? Here's the terminal, right? I'm in the docs directory. I will use the command make space HTML. Right? Do that and enter, and Sphinx does its thing. Okay. Well, what exactly has it done? Well, if you look at the output here, it says that the HTML pages are in _build /HTML, right? So if we go ahead and see, there is this _build directory. So if we say, okay, let's go _build, what's in HTML? And if we look here, we see some HTML files, including this index.html, which remember, that's what we set as our root, as our home doc. Okay, so let's go ahead and let's open index.html in a web browser. Right? If you're on a Mac, there's kind of a shortcut you can use to do this. It's just the command, you can use the command open, and then you could do open build HTML and then index.html. But if you're not on a Mac, I'm sure there's some other shortcut you can use, but you can always just from a web browser page, you can just open a new tab and say in Chrome here, file, open file, right? And here you can navigate to your index.html and open it kind of manually, just like that. Okay? But here, I'm just going to use this open command. Okay. And here's what we see. Here's the contents of index.html, and you may recognize this format. It looks similar to, I don't know, NumPy, SciPy, maybe, or other packages maybe you use. This is a very common format. Okay, great. So it looks, oh, question. Oh, you mean these links down here? They're usually set up by default. If they're not there, we can, so it's not critical. So those links aren't critical. It's something we can debug later, maybe. Yeah.
I think if you don't see the links, it might be that the docs aren't building properly too. So that's something we can, this Sphinx is notoriously like tricky, so we'll help you debug it.
Great. Okay, great. Okay, well, if we take a close look at these docs, we'll notice that they look pretty, but there's no content in them, right? This is empty. Okay, so let's go ahead and let's go back to VS Code. And now let's add the content that we want to add. And if we're following along with the README, sorry, I'll just keep this along here. We're now on step 7. Okay. So, I mentioned before, the way Sphinx works is that it wants to read these .rst restructured text files, and it'll convert them into our HTML pages. So let's go ahead and make a .rst file for correlate.py in our package, right? So let's see. We can do that from the VS Code window, right? We can add the new file button under docs here. And let's go ahead and make a new file, correlate.rst. Okay, that'll add a blank page here. Okay, now inside correlate.rst, let's go ahead and copy this whole block of text under step 7 in the demo. Right? I'll talk about that, what that means in a second. Let's go ahead and copy it in. Okay, so this is kind of the commands that Sphinx expects. Let's see, do I have it? Oh, yeah, nice. I broke it down in a nice screenshot here. This is just a screenshot of what we just did. Okay, what are the different parts of what we of this block? Okay, so at the top of the file, you have this like ... underscore correlation colon. You can think of that as like the label for this .rst file, right? This is just like in LaTeX, right? You can label figures and label tables, and then you can refer to them in the text, and it makes a link. This is kind of like setting up the link to this RST file that you can use to build links elsewhere in your documentation. So that's just the label. The next part here, we have these correlation functions and then these equal signs and some text here. This is the title of your documentation page and just some text just to describe what's going to go on the documentation page, right? So we're talking about correlation functions, and in here, these are functions to perform correlations. This is all restructured text format. I'll talk more about different fun things you can do in RST in this format later on in the lesson. Okay. Now, the last part of what we just did, this is where all the Sphinx magic is. This is this ... auto module, colon, right? This is telling Sphinx to look at, follow the path, find correlate.py, and automatically parse the doc strings of all the members, all the functions inside the function itself. So I'm not going to go into a lot of details right now. There's fancy things you can do, like you can tell Sphinx only document specific functions on the web page. There's lots of things you can do, but for now, this is just saying document all of the functions I see inside correlate.py. Okay, great. And that is all we need inside correlate.rst. Okay, we're almost there. Now we've made our correlate.rst. The last thing we want to do is we want to link correlate.rst into our root of our documentation page, right? We want to put a reference to it inside index.rst. So let's go ahead and open index.rst. Oh, whoops, this out of the way over here. Let's go ahead and open index.rsc in our VS Code. All right. Should, if everything's worked properly, you're going to see a file that looks like this. And what we're going to do next is you'll see this section that's like .. talk tree. Talk tree, that's table of contents tree. We're going to add correlate.rst into our table of contents. How do we do that? Well, we can go ahead and just somewhere under this talk tree thing here, we want to add correlate.rst. Now, something to be careful with, you have to be really careful with spacing in Sphinx, kind of in all cases. We're going to add correlate.rst 3 spaces from the new line so it matches the indentation depth of these other commands. The other commands here, I'm not going to talk about. I have some extra details at the end if you're interested. But okay. So now we've made correlate.rst. We've added it to our index.rst file. Now we're all set to make a new version of our documentation, right? And for that, we'll just go back to our terminal, right? We're in the docs directory. We'll just rerun the command, make space HTML. And now, if everything works, Sphinx does its thing, and it's remade the documentation pages inside this _build HTML. Okay, well, what happened? Well, let's go back to the web browser. And we remember we opened index.html before. Let's go ahead and refresh the page. So open the new file. And now, just like magic, we have documentation, right? Okay, here we go, right? Correlation functions. It says these are the things under correlation functions. You know, that's neat. Let's go ahead and follow the link, right? We click correlation functions. Now look, all of the doc strings that you painfully wrote and followed all the spaces and all the rules, now it's just nicely formatted in a way that your user can appreciate. So it is, so Sphinx can be very finicky. It's very kind of, you'll run into syntax, 8 out of 10 times if you're running into errors with Sphinx, it's because of some sort of syntax thing. But once you get all the syntax to work, it is like magic. And it's very pretty. And, folks can search the docs like, oh, what is this cross-core function? Oh, look, here's the link. Ah, there's my API, right? And this is how your user can interface with your code. Okay. Yeah, so that's kind of the quick demo. And once again, Sphinx can be tricky. We're going to have some time now to make sure everyone can do the demo on their own, and I'm going to talk about an activity in a moment. But before I release everyone, I wanted to go over some tips and tricks for Sphinx. This is at the bottom of the README. First thing, remember to check out kind of this link that shows additional Google-style docstring examples for how to document different specific cases in your code, like optional input variables, classes, exceptions, so on and so forth. In addition, right, we've been using these .rst files. So far, we only had, I don't know, like headers and some basic formatting things, but you can actually have lots of different formatting inside .rst files. And we've included a nice little cheat sheet if you want to know how to make like bulleted lists or subheadings. Go ahead, check out that cheat sheet there. And then finally, I'll just reiterate again, Sphinx is super finicky with all the spacing and the syntax. You'll note, like in the README, there's like, oh, I have to make sure I have to have a space here. After auto module, I need 2 colons, not 1 colon. Just be super careful. Oftentimes, if Sphinx isn't working, it's something with this syntax that's going wrong. So we've tried to, in this demo, model how that syntax works. But if you run into problems, please ask a TA, instructors, please ask us, and we'll try to help.
I'll tell you also, like, the way that I debug Sphinx issues is I pull up an example that's working and put it next to the thing that's not working and just go line by line. That's the only way I've found to like actually like make it work.
Yes. Yeah, absolutely. Okay, and then there's some more details on Sphinx commands I don't think I'm going to get into here. Okay, but let's jump into our activity. Okay, so let's break up into groups. Let's make sure once everyone can kind of reproduce the demo that we just did, we want folks to document at least one function in your package using this docstring format that we set up. And then once you have your doc string, try to set up Sphinx documentation and build the documentation for your package, just like we just did in the demo, right? And if you're kind of confused as to where to begin with this, in the demo, just you can hop back to step 2, right? We want to go ahead, make dir docs. That's like a good starting point. In your repo, you want to start there and go through the Sphinx instructions. Okay. With that, I think we'll have, what would you say, like a half an hour, 30 or? Okay. Yeah. Let's do. Yeah. Okay. Let's go 40 minutes. So let's reconvene at 45 after the hour to wrap up. But yeah. Once again, if you have questions working on this activity, please don't hesitate to ask us. So thanks. So hi everyone. Welcome back. Hopefully, I was hearing some good things. Hopefully, we were making some progress on the docs. Once again, I'll just reiterate, right? Sphinx can be very finicky, so don't worry if it's still a little buggy, you don't have it quite working yet. Feel free to continue to ask questions to the TAs and to us, and we'll help you get everything working. Yeah, so we're going to end actually a little early today. We're ahead of schedule. So I just wanted to remind folks that tonight, remember, we have for the in-person folks, we have our dinner out on the lawn together. And that lawn specifically, it's just this big green space next to the Learning Center right here. And so otherwise, for the afternoon, you have it completely off. Take some time to relax, enjoy yourself, and I'm looking forward to seeing everyone at dinner. So thanks, everyone. Okay. And thanks, everyone online.